Great. So welcome everyone to our OpenSim webinar. My name is Jennifer Hicks. I'm the OpenSim R&D Manager and also the Associate Director of our National Center for Simulation and Rehab Research. And I'll be serving as the moderator for today's webinar. And I'm pleased to welcome today's presenters. So Adrian Lai is joining us from Simon Fraser University and Allison Arnold from Harvard University. And they'll be presenting on why our antagonists co-activated in my simulations, simulating cycling and other high flexion tasks. So next slide. Before we get started, I want to review the goals of the OpenSim webinar series. So the OpenSim software is a freely available application for visualizing musculoskeletal structures and simulating movements of both humans and animals. So the first goal of our webinar series is to showcase the wide range of cutting-edge research that's being performed with OpenSim. OpenSim is also a growing and diverse community of users, and so the second goal of our webinar series is to provide a platform for the OpenSim community to communicate and collaborate. Next slide. Before we get started, a few quick reminders about the format of the webinar. So we definitely want to have plenty of time for questions, but we'll address those at the end of the presentation using the text-based Q&A panel. If you need any additional technical help, you can also consult the guide on our website. Next slide. So now I'd like to go ahead and introduce our speakers for today's webinar. So first, Adrian Lai is a 2017 NCSRR visiting scholar, so we were lucky to just have him on the Stanford campus for a few weeks working with us. And he's a postdoctoral fellow at Simon Fraser University. Adrian has a PhD in mechanical engineering from the University of Melbourne. Allison Arnold is a research scientist at the Concord Field Station at Harvard University. And her PhD is in biomedical engineering from Northwestern University. And an important goal of their NIH-funded research in collaboration with James Wakeling and Andy Bewiner is to test and refine predictions of hill-type muscle models within simulations of cycling and jumping. And so we'll hear more about their efforts to this end in their webinar today. I'm looking forward to it, and with that, I'll let you guys take it away.
All right, thanks, Jen. Hi, everybody. Thanks for joining us. And thanks to the OpenSim team for the chance to share our work. Before we start, I'd just like to let everyone know that this work is summarized in a paper, which is now available in the Annals of Biomedical Engineering. And also, if you're interested, we've posted a model that you can download on sim2k.org. So why simulate cycling? Cycling is popular for recreation and for transportation. It's practiced at the very highest level of sport, and it's often prescribed for exercise and for rehabilitation. Like walking, pedaling involves reciprocal flexion and extension of the hips, knees, and ankles. However, it avoids the loading that we associate with foot-ground contact. And if subjects are strapped into a stationary ergometer, then it minimizes some of those balance demands. So there are good reasons why the biomechanics of pedaling have been studied for decades. Now, as an experimental paradigm, pedaling is really interesting because cadence and load can be varied independently. This means that basically with the same kinematics, we can change the mechanical demands of the task. One of the longer-term goals of our work is to predict patterns of neural excitation that we see experimentally across different cycling conditions. And to do this, we suspect that we may need to develop new hill-type models that we can tune to represent slower and faster fibers, or we may need to consider cost functions or to implement cost functions that consider metabolic cost. So our team's interested in testing muscle models and improving estimates of muscle force. Now, as a first step, we decided to generate some muscle-driven simulations of pedaling. And our specific aims were to predict kinematics that accurately track our subject's motions and predict muscle activations that reproduce our subject's measured EMG data. And if you're using OpenSim, this is often what you're trying to do. Now for pedaling, we found out that doing this was harder than we expected. And so our goal for today in the webinar is to just share some tips that we learned for simulating tasks like pedaling that have substantial hip and knee flexion. So here's our outline. I'm going to briefly describe our experimental data. Then I'll go through the scaling and inverse kinematic steps, and I'll talk specifically about some of the challenges we had to deal with related to the high hip and knee flexion. Then Adrian will take over, and he'll show you results from our very first attempt to simulate pedaling, and those results weren't very good. So he'll explain how we changed the model to decrease passive force, and then we'll show you how these changes improved our simulations. So the cycling data we used was originally collected by Taylor Dick as part of her PhD thesis at Simon Fraser University. Taylor tested 20 elite cyclists at 11 different combinations of cadence and load, and this was all done on an instrument cycling ergometer. For each subject, she tracked 32 markers. She measured reaction forces, both normal and radial to the crank. She recorded EMG from 10 muscles, and she recorded ultrasound images of the medial and lateral gastrocnemius. And so from these images, we can go back and estimate length changes of the muscle fibers, and we can track motions of the muscle tendon junctions. Now for today, we're going to show results from one cyclist who pedaled at 80 RPM at a power of 200 watts. And this condition is basically in the middle of the conditions that Taylor tested. So the first thing we did was we wrote some MATLAB code to add virtual markers to our marker set. A virtual marker is a marker that we didn't actually track in our experiments, but we can locate it based on other markers that we did track or known geometry. So for example, we can't easily put a marker at the subject's hip centers, but we can estimate hip centers from the motions of other markers. And then we can use these hip centers to scale the model's pelvis width or femur length to our subject. So for this study, we estimated subject hip centers using the pivoting algorithm that was described by Rob Sisson and Scott Delp. We analyzed cycling trials to calculate the sagittal plane coordinates of the hip centers, and we used circumduction trials to get the frontal plane coordinates. We also added virtual markers at the pedal axis and at the pedal center of pressure, and this was based on known geometry of our bike. These markers helped us check whether we were applying the measured reaction forces at the right locations when we were running inverse dynamics. So now that we've processed our data, we're ready to run it through the OpenSim workflow. So our plan is to scale a generic model to our subject, calculate joint angles and net joint moments, solve for the muscle excitations and activations that track these data, and then compare these to our subject's measured EMG recordings. Now to do this, we need an appropriate model. And so for this study, we chose the model that was published by Apurva Rajagopal and her colleagues because it seemed like the most up-to-date model available, and it was designed for conducting simulations. Now, at the very first step, before we even get to dynamics, we ran into some challenges. During pedaling, the hip flexes to about 90 degrees, and the knee flexes as much as 130 degrees. And at these joint angles, our marker data showed some significant skin motion artifact. Also, Rajagopal's model has been shown to work really well for walking, but it was never designed to operate over these ranges of motion. So we can't scale the model to our subject or solve for the joint angles until we've dealt with these challenges. For those of you who may be new to OpenSim, I'm going to briefly review what the scale tool does. So we have a generic model, and we want to scale it to our subject. For this study, because we were focusing on the lower limbs, we removed the head, arms, and torso from the generic model, and we lumped their massive pelvis. We can use the scale tool to scale the dimensions of the body segments based on distances between marker pairs. We can also use the scale tool to move markers on the scaled model to match their measured locations in a static trial. And this is especially useful when we have clusters of markers that aren't directly over landmarks, and so we don't know exactly where they should go, but we want to track them. The scale tool also adjusts the mass and inertial properties of the bodies, and it will scale muscle fiber length and tendon length. So we did several things to deal with the skin motion artifact when mapping markers to our model. First, we went back to our pre-processing code and we added some virtual knee markers. We calculated where we thought the knee markers should have been by enforcing the thigh and shank lengths to be constant. And we did this because our actual knee marker and our clusters of markers on the thigh and the shank weren't reliable over the entire pedal cycle. Our next strategy was to scale the model in 2 steps. So in walking, you often have a standing calibration trial, but in this study, we collected our static trials with subjects seated on the bike. And that's because we needed to know where the feet were relative to the pedals. The only problem with that is that on a bike, one leg is straight while the other leg is flexed, and many of the markers shift with flexion. So we collected two static trials, one with the right leg at bottom dead center and one with the left leg at bottom dead center. We scaled the whole model based on the right leg markers with the right leg extended, and we mapped all of the right leg markers to the model at this position. Then we ran the scale tool again without changing the model size to map all the left leg markers to the model when the left leg was extended. And then our last strategy when tracking the subject's kinematics was to assign high weights to the markers that we had the most confidence in. So these are markers at the pedals, at the joint centers, and the pelvis clusters. And these markers were not really affected by skin motion artifact. So we'll show you the inverse kinematic solution for one trial. The pink markers are fixed to our model, and the blue markers are our experimental data. And you can see that even though there's substantial skin motion artifact, the pelvis cluster and the pedal markers are tracking really well. Now, as I said before, the model we're using was designed to study walking, but our cyclists flex the knees over a much wider range of motion. So our next step was to increase the model's range of motion. So we did this, but unfortunately, we found that the paths of several muscles failed at these high knee angles. So for example, the biceps from a short head, which is normally a knee flexor, we found out that it started lengthening as the knee was flexed. And we also saw that the vastus lateralis just fell off its wrapping surface. So we had to tweak the muscle paths to fix these issues. In the process, we also corrected a discrepancy in the tibiofemoral translations. So you can see here in the existing model, the tibia starts translating away from the femur when the knee is highly flexed. So to investigate this, we went back and we plotted the X, Y, and Z translations of the tibia with respect to the femur. And we did this for the Rajagopal model, which is shown here in red. And that was based on Edith Arnold's 2010 model. And then we also went back and we plotted the tibiofemoral translations for Edith Arnold's 2009 model, which she implemented in SIM. And you can see that the translations are different, particularly when the knee gets to those high flexion angles. So for this study, we decided to go back and implement the knee from Edith Arnold's 2009 model because we felt that it better reproduced the measured data published by Peter Walker, especially at those high knee flexion angles. So here are the moment arms of knee muscles plotted versus knee angle. The red curves are from the Rajagopal model, and we've extrapolated these out to 140 degrees, which is something she never did, but we needed the model to work at those angles. The blue curves are from our new model, and the gray curves show data that was published by Buford and colleagues from tendon travel experiments. And so basically what we tried to do was keep the existing model's moment arms near full knee extension, but improve them at high angles of knee flexion. So now at this point, we've dealt with skin motion artifacts and we've tuned the model, but we've got one more problem related to the kinematics. We noticed that we could predict different ankle angles depending on how we weighted markers at the feet. For our studies, we care a lot about ankle angle because ultimately we want to predict force sharing among the plantar flexors across different cycling conditions. But in the scale tool and in the IKE tool, by tweaking the marker weights, we were getting ankle angles that varied by as much as 10 degrees. Now, part of the problem in our case was caused by our subjects wearing sandals, and there was definitely some uncertainty in the marker locations due to this. So to better resolve ankle angle, what we did was we went back to our pre-processing code, and we added a virtual marker at the sandal surface, which we could estimate from our known pedal and sandal dimensions. This let us estimate the subject's ankle angle in the static trials, and then in the scale tool, we could include this ankle angle in the cost function when we were placing the model's markers. Now, the last thing we needed to do before moving on to dynamics was to update the scaled model's mass and inertial properties. We updated properties of the right tibia to account for our ultrasound probe, and we updated properties of the feet to account for the sandals, cleats, and pedals. And just a note, we couldn't make these changes to the generic model because all this added mass is fixed and we didn't want to scale it. Also, the position of the probe on the leg varied from subject to subject, so we had to run scale first and then go in and update each of our scaled models. So finally at this point, we have a scaling and an inverse kinematics procedure that works well. We've tested it on all 20 of our subjects. And I'm going to turn the talk over to Adrian, who will tell you about predicting the muscle activations.
Cool. Thanks, Allison. So at this point, we had a model that we had refined knee kinematics and more experimentally consistent muscle tendon unit paths and moment arms. So we also had accurate joint angles from inverse kinematics and all the tweaks that we made with our virtual model markers. So we were now ready to generate some muscle-driven simulations of pedaling. To do so, we followed the standard OpenSim workflow to generate muscle-driven simulations. So firstly, we solved the equations of motion of the model using inverse dynamics and obtained a set of net joint moments around each degree of freedom. We made sure that our net joint moments were comparable with previous experimental studies of pedaling. Next, we used OpenSim's residual reduction algorithm to obtain a set of kinematics that were more dynamically consistent with the measured ground reaction forces. We made sure that the changes in the kinematics and residual forces were within the tolerances recommended by the OpenSim team. Finally, we used OpenSim's computed muscle control algorithm to predict a set of neuroexcitations constrained by the force, length, velocity properties of the muscle that reproduce the subject's measured movement dynamics. Because CMC is also using a tracking PD controller, we also made sure that the resultant kinematics and residual forces were within the recommended tolerances. So here are our simulations of our initial attempts to generate subject-specific simulations of pedaling. And you can see everything in the simulation was consistent with our experimental data. We were therefore pleasantly surprised that our initial attempts of simulating pedaling failed to reproduce some of the subject's measured EMG recordings. So here are our EMG signals plotted against our model predicted muscle activations from 10 lower limb muscles. These initial simulations used models with the refined knee kinematics, but had the same force-generating properties as those specified by Rajagopal and colleagues. One thing to note is that the EMG signals represent the neuroexcitation, while the model predictions represent muscle activations. So there might be some discrepancies due to excitation activation dynamics. Nevertheless, you can see some that muscle activations in the gluteus maximus and the vastus medialis were mismatched. You can also see some anomalous coactivation in the rectus femoris, biceps femoris, medial gastrocnemius, and the lateral gastrocnemius. The common link between all these muscles were that they were all hip and knee flexors, and most of the coactivation occurred during the upstroke phase of pedaling, when the hip was flexed, the knee was flexed, and the ankle was in a neutral or plantar flex position. So before we could use the model for future simulations, we wanted to determine the potential sources of these discrepancies between the muscle activations and the predicted by the model and the measured EMG data. One thing we noticed was that when we ran static optimization in OpenSim, a significant portion of the anomalous coactivation disappeared. So based on this observation, we isolated the problem to 4 possible reasons. It could have been the algorithm used to predict muscle activations, i.e. static optimization versus computed muscle control. It could have been due to the rigid tendon assumption in static optimization, where there is a direct relationship between muscle tendon unit and muscle fiber dynamics, while in CMC, a computed compliant tendon is implemented, providing a non-linear series elastic element for the muscle fiber to account for. It could also be the excitation activation dynamics included in CMC, or it could be passive forces. We found that in the static optimization algorithm implemented in OpenSim, it actually neglected the passive force length properties of muscles, so only predicted the muscle force according to the active force length and force velocity curves. So we ran a series of simulations with different setups, and we ended up eliminating the algorithm, tendon compliance, and activation dynamics as the primary sources of these excessive coactivations. And this led us the passive fiber forces as the main culprit for the discrepancy. Specifically, it was the passive force generated by 8 muscle tendon units that were the most problematic. They were the 3 compartments of the gluteus maximus, the 3 vasti muscles, the lateralis, medialis, and intermedius, the rectus femoris, and the soleus. So how are passive forces modeled in our model? So let's go back to a schematic of a hill-type muscle model, and the basic components of the hill-type muscle model are the series elastic element, the active contractile element, and the passive elastic element. So the part that we're interested in is the parallel elastic element. So the passive elastic element is typically represented as a nonlinear force length curve, which is normalized by the muscle's maximum isometric force and optimal fiber length. The current curve implemented in the Millard muscle model is the Quintet-Bezier curve, and so to reduce the excessive passive fiber force, we needed to either alter this curve or the inputs that go into calculating passive forces. There were three options for reducing passive force. You can either increase the fiber strain at maximum isometric force, lengthen optimal fiber length, or lengthen tendon slack length, and we'll go through each one of these options now. So the first option was to tweak the fiber strain at maximum isometric force. And this value is currently set at 1.7 by default in the Millard muscle model. And if this value of strain is increased, for example, to 1.9, this would flatten the passive force length curve. So for a given normalized length, less passive force will be generated. This was the easiest modification to make to reduce the passive forces, but all available experimental data suggested that the curve should actually be more steep than the one that we use in the model, such as the passive force length curve reported by Roots and colleagues for a bundle of rat muscle. The second option was to adjust optimal fiber length, because for a given fiber length, a longer optimal length would shift the normalized length leftwards towards a lower passive force. However, we were hesitant to change the optimal fiber length because it is a measurable value scaled from the best available experimental measurements of sarcomere length. The third and final option was to adjust tendon slack length. This tweak works similar to adjusting the optimal fiber length, but instead the absolute fiber length in the length equilibrium equation would be reduced. Because tendon slack length is not measured experimentally, but rather derived based on fiber lengths measured at the reference position, we ultimately chose to primarily adjust this parameter before considering the other two options. So we varied tendon slack length within one standard deviation of the expected variation reported by Rajagopal and colleagues, and at the same time we ensured that our normalized fiber lengths at the reference codes remained within one standard deviation of the lengths reported by Ward et al. We also refined the optimal fiber lengths in the vasti muscles to match estimates of in vivo measurements of sarcomere lengths reported by Chen and colleagues, where they used microendoscopy to measure sarcomere lengths at given knee angles. So here we have the net passive moments around the hip, knee, and ankle as a function of joint angle obtained from the initial and refined models, compared with experimentally measured passive moments reported by Reiner and Edrich. You can see that the net passive moments around all three joints using the refined model match better with the experimental data than the initial model. From our initial simulations, we also noted that some muscles like the medial and lateral gastrocnemiae became too short to generate active force during portions of the cycle that involved substantial hip and knee flexion. Specifically, if you look at the active force length curve, these muscles were hitting the base of their ascending limb, which is not physiological. So we ended up modifying some of the force generating properties, attachment points, and wrapping surfaces of these muscles as needed to bring the muscle fibers to operate over a more reasonable range of the active force length curve. Our changes were not arbitrary, but guided by experimental moment arms, especially experimental data reported by Hirasa and colleagues, who reported ankle angles when the onset of passive force occurred, which we assumed was when the fiber was at optimal length. After altering the force generating properties of the gastrocnemiae, we were able to obtain fiber lengths during pedaling that conserved the length profiles, reduced the excursion, and was off the base of the force length curve. So after all these modifications to the generic musculoskeletal model, we ran the subject-specific muscle-driven simulations of pedaling to see if there were reductions in the passive forces resulting in the reduction in the anomalous coactivation and more comparable muscle activations with EMG signals. So what did we find? So here are the net joint moments around the hip and knee. You can clearly identify the downstroke and upstroke phases as the knee and hip extend and flex. So here are the contributions of the active and passive net moments, the hip and knee, using the initial model. You can clearly see that in both joints there's substantial net passive moments, and as a consequence, compensatory active moments were necessary so that the simulation reproduced the net joint moments from inverse dynamics. So here are the same active and passive moment contributions using our refined model. You can clearly see a decrease in the net passive moments both at the start of the downstroke and throughout the upstroke phases of pedaling. And as a result, the net active moment were diminished significantly in both the hip and knee. This led to a decrease in the anomalous coactivation in the hip and knee flexors, where you can clearly see differences in the coactivation in the rectus femoris, the biceps femoris, and the medial gastrocnemius and the lateral gastrocnemius. We also obtain more consistent muscle activations compared to EMG in the gluteus maximus and the vastus medialis. So after observing these reductions during pedaling, we wanted to investigate if this passive force problem was systematic across different movements. So we expanded our project to include walking and running simulations. So we had data from a previous walking and running study that we conducted, and if you'd like more information about the experimental data collection, I put a reference at the bottom of this slide. Briefly, we used motion capture and ground reaction forces from one subject walking and running on an instrumented treadmill at 1.4 and 4 meters per second respectively. We then extracted 5 gait cycles and ran it through the standard OpenSim workflow from inverse kinematics to CMC to obtain muscle-driven simulations. In our initial simulations, we again saw anomalous coactivation during early and mid-swing phases for both walking and running. So when we looked at the same net joint moments of the hip and knee during running, we saw the same trends as what you see in pedaling, where during early to mid-swing phase of running, using the refined model, there was a reduction in the net passive moments at the knee. This resulted in a reduction of the anomalous coactivation in the knee flexors, particularly in the semitendinosus, the medial gastrocnemius, and the lateral gastrocnemius. Lastly, for walking, we again saw excessive passive forces during early to mid-swing phase, and by using the refined model, we were able to reduce the net passive moments and the compensatory net active moments. For walking, muscle activations were not influenced as much as we expected for using the refined model, but we were able to obtain net passive moments at the hip and knee that were more consistent with the previous experimental study by Whittington and colleagues, who reported experimental net passive moments during walking. So in summary, our refined musculoskeletal model reduced excessive passive forces, reduced anomalous coactivation, and yielded more physiologically consistent muscle activations when compared with EMG recordings during pedaling, running, and walking. We also extended the functional range of motion in the model, making it more applicable for cycling and other movements that involve high hip and knee flexions, such as sprinting, rowing, and deep squat exercises. So in conclusion, having robust off-the-shelf models is unquestionably appealing, but they need to be tested in the context of their intended use before they can be applied to investigate new research questions. We believe our refined model is part of an iterative process towards improving musculoskeletal models in OpenSim and adapting them to different applications. We encourage others to make additional refinements to our model and share them with the community. So here is just some future challenges to address if you're looking at refining the model. So in the net passive hip moments may still actually be too large. So we found that even though our net passive moments at the hip were much more consistent than the initial model, we believe it should be reduced further by, for example, including a more sophisticated model of the iliotibial band. So that could insert directly onto the gluteus maximus, which currently has a rigid tendon, and it could possibly reduce overestimating of muscle fiber length changes in this muscle. We also found that even though we improved the operating fiber lengths in the gastrocnemiae, the amount of excursion in these muscles were far greater than what was reported in vivo ultrasound studies during corresponding movements. Further improvements to the muscle's 3D geometric paths are required before we can be reasonably confident in the predicted operating regions of these muscles on their force length and force velocity curves. So the model is available on our SimTK project page, as Alison mentioned at the start of the talk, and it comes in 3 configurations. It has the lower limb only, it has a torso with the lower limb, and finally the entire skeletal model with torque actuated upper limbs. Finally, we'd like to acknowledge our collaborators and thank our funding sources, and we're happy to take any questions. Thank you.
All right, thanks Adrian and Alison for a great talk. Thank you for highlighting some really important points about using models and improving models that the community shares, and thanks for sharing all your work with the community as well. At this point, we can go ahead and open up to questions. So if you have questions, you need to find the Q&A panel on in your webinar controls and go ahead and type in your question and make sure you select to ask all panelists. All right. I guess one question while we're waiting for others to come in. You guys have been doing modeling and simulation for a long time, and so we're able to draw on that expertise and coming up with that list of what the possible sources of error might be and how to fix it. Do you have suggestions for how people who may be a little more new to modeling and simulation can start to build up some of the same lists and some of the same knowledge?
I guess I would say that the best way is probably start simple. Having like a really complicated like a multi-driven simulation with multiple muscles can be quite daunting. So having simple simulations where you have maybe just a one muscle tendon unit actuator, and then understanding all the different components that go into it and how each variable can affect your ultimate answer would be probably the best place to start.
Mm-hmm. And I would just add to that, just question, if something doesn't look right, just because OpenSim predicted it, don't assume that it's right, question it. So for us, when we started seeing passive force, I mean, you don't even have to do a simulation. If you just take the model and flex the knee and look at what the passive forces are, when the knee is really flexed, the forces can get really large and they're just not plausible over those ranges of motion. And there's experimental data you can go and check and see how it compares to what you find in the literature. But I would just say you just have to really question every step.
Mm-hmm. Great. So now we have some questions from the audience as well. One is, you mentioned that when you're using a model that someone else has developed, that you need to be sure that it's also will work in your setting and to test it for the applications that you're interested in. Do you guys think that your model would be appropriate for studying movements such as a deep squat? And if not, what kind of other tests and validation would you suggest?
So the current model, the muscle paths work up to about 140 degrees of knee flexion. And so if you're squatting beyond that, I expect you will have problems. The way that the vasti are implemented, they wrap over a wrapping surface, and it's hard to get the vasti to stay on the wrapping surface as you flex further and further. So there may be a way to simplify the wrapping at those deep knee angles, but I would take a really close look at the muscle paths and the muscle moment arms at the knee angles that you care about. And if you see a discontinuity in the muscle moment arm, if you plot it, you'll know that it fell off the wrapping surface and you need to fix it.
Mm-hmm. So that question was from Bass Van Horen, and there's a related question to the first question and your answer, Allison. This is a question from Danilo Catelli. It's a great talk. I've been applying Rajagopal's model for deep squatting tasks. Did you apply any additional wrapping surfaces to avoid muscle crossing the bone on your high flexion angles?
So you can download our model and look. We didn't want to add wrapping. I felt like Apoorva had done a really good job to try to simplify some of the wrapping that had been there in Edith Arnold's model, because the more wrapping you have, then it slows down your simulations. So Apoorva done a really good job of trying to use sort of a minimal set of wrapping, and we basically just tried to tweak those, or maybe even get rid of, like at the biceps from a short head, we actually got rid of a wrapping surface to better match measured EMG data. So I don't necessarily recommend adding a lot of wrapping. Wrapping just makes it more complicated. Wrap where you need to, but in some cases it may be better to eliminate wrapping over the, or maybe you just analyze a portion of the motion where the knee is really flexed, and then you might need a different wrapping surface than what you would need when the knee is extended, for example. So adding wrapping doesn't always help you.
Right. Let's see. So while we're waiting to see if there are any other audience questions, I'll go ahead and ask another. So you mentioned that another possible issue with the model is with how the IT band is represented. Could you go back to those slides and talk a little bit more about if you guys have ideas about how that might be resolved in the model?
We do. This is work that Carolyn Eng did for her PhD thesis at Harvard. So we have a preliminary model of the gluteus maximus and the tensor fascia lata attaching to the IT band. And Carolyn did some detailed dissections in cadavers to figure out how much of the gluteus maximus mass is attaching. She measured muscle moment arms using tendon displacement, moment arms of these paths as they insert into the IT band. So we have a model, but we haven't yet incorporated it into our simulation. So it's something that we're working on. But the current existing model in the GMAX, the tendon is stiff and it attaches to the femur, and we just know from our cadaver studies that a large portion of this muscle, which can produce a lot of force, attaches to the IT band, and the IT band is more compliant than tendon. We've measured, Carolyn measured the compliance of IT band, so we modified the tendon force length properties in the model. We just haven't put it all together yet, but it's, and so we don't know. I suspect it will change where the gluteus maximus is operating over its force length and velocity curve, but we haven't actually done the simulations.
So just adding to what Allison was just saying, so I think one of the problematic muscles that we saw in these passive forces was the Gmax, all three compartments. So we did change the optimal the tendon slack length for those three muscle tendon units, but they had to be within the experimental studies, and so if you connect it to a rigid tendon, you sort of you have to compensate for that by lengthening the fibers over a larger portion of their operating region. So if you have some sort of compliance in the tendon, it would always reduce the excursion, so they're more likely to have less passive forces and therefore make it more reasonable over a range of flexion angles.
All right, so I think we've addressed all the questions. So if you guys could advance the last couple slides at the end. So thank you again for the great talk, you guys, and the discussion. I want to acknowledge that OpenSim, this webinar series, are supported by several grants from the NIH, including an NIH grant that funds our National Center for Simulation and Rehab Research. Next slide. If you'd like to get more information about the NCSRR, upcoming events, and other resources for the OpenSim community, those are available at our website. We also ask that you fill out the survey that will appear in a pop-up window at the conclusion of the webinar. And this will help us improve the webinar series and choose upcoming topics. So thank you again to everyone for participating. Thank you, Allison and Adrian, for putting together a really clear and informative talk, and also for publishing the paper and sharing the models openly with the community. We're always really excited to see that. We'll send out a follow-up email that has links to relevant paper and SimTK project, and a recording of the webinar in case you want to review anything that was discussed today. And with that, I'll go ahead and close up the webinar. Thank you again, and we hope you all will continue to stay involved with OpenSim.